Hello calculus fans. Today we will look at exponential growth and decay, which is section 3.8 in the Stewart textbook. In many natural phenomena, quantities grow or decay at a rate proportional to their size. So as an example, we could consider population growth. So in the United States, the 2010 population was around 310 million, and the population grows by maybe, let's say, 3.1 million per year. And then if you compare that to a small town like Sand Lake, Michigan, the population was 499. Maybe the population there grows by 2 per year. So the growth rate here is proportional to the size, right? A large population has large growth, small population, small growth. So if f of t is the number of people in a population, it seems reasonable that the rate of growth f prime of t, so the rate of growth to be like in people per year, is proportional to the population f of t. In other words, f prime of t equals k times f of t for some constant k. So the derivative is proportional to the original population, right? Because the derivative is the original population times some number k. As another example, we have radioactive decay, which we'll talk about later. We're going to talk about carbon-14 dating. It just says that the mass of a radioactive substance decays at a rate proportional to the mass. Physicists express the rate of decay in terms of half-lives, which is the time required for half of any given quantity to decay. And by decay, it doesn't mean it just disappears. It typically turns into something else, as we'll see later. And let's look at one more example. So let's say Bill Gates stops by our college and wants to open an account in the bank nearby. And we also want to open our Math 133 class savings account. Each of these accounts, let's say, will be at 1.45% compounded monthly for 10 years. So Bill Gates, let's say his initial amount is $1 million. And let's say our initial amount, we put all of our money together and we have $155. Well, at the end of the 10-year period, Bill Gates will have earned some interest in the amount of $155,938.38. And you could calculate that just using the compound interest formula. Our class, on the other hand, won't fare quite so well, but we will have earned $24.17 in that same 10-year time period. In case you're curious, here is the compound interest formula where you have the amount equals the principal, the amount you invested, and then here we've got 1 plus r over n. R is the interest rate as a decimal, so you always have to write it as a decimal. N, which is here and here, these are the number of compounding periods per year, which would be 12 in our case because it's monthly, and t is the time always in years. In order to understand exponential growth and decay, we have to understand the law of natural growth or decay. So let's say y of t is the value of a quantity y at some time t, and if the rate of change of y with respect to t is proportional to its size, y of t at any time, then we have this. And this just basically says y prime equals k times y. So the derivative of y, the rate of change of y, is proportional to y itself, right? Because k is just some constant. So if k is greater than 0, then you have growth. And if k is less than 0, then you have decay. And this k is referred to as the relative growth rate. So you can see if k is a positive number, you're going to have growth because then the rate of change is equal to some positive number times y itself, right? dy dt equals k times y. And this is actually a differential equation. So this right here is a differential equation. Some of you who are super lucky will take a course in differential equations, and this will be a pretty simple one. Differential equation is just an equation that has a derivative in it. And what's different about that is, like when you're in algebra, you solve an equation, you get a number, like, oh, I solved the equation, x was 5/3. But when you solve a differential equation, you get a function. So it's definitely different. You solve a differential equation and you get like y equals something. Y equals 3x plus 4, something like that. So the answer to a differential equation is actually a function. It's a function that when you plug it back into the differential equation, it satisfies the differential equation. But we don't need to know that at this point. Or maybe we do. This question says, can we find a solution to this differential equation? Well, I can tell you, when you take a course in differential equations, you'll have a technique called separation of variables that will actually solve this directly. But for us, what we're going to do, okay, it says, can we find a solution? We're gonna make an educated guess. It's going to turn out to be correct in this case. Okay, we're gonna guess the solution based on what we know. And here's what we can think. Notice that if a function satisfies this, like think if I took the derivative of y and y came back, can you think of an equation like that or a function that works that way? So, like what about y equals, well, think of what function. Look at your derivative sheet. When you take a derivative of a function, there's one particular function that comes back completely unchanged, right? Like, if y equals e to the x, y prime is also e to the x. So there might be some sort of, maybe this. What if we have something like c e to the kt? Okay, so since we're using t is our independent variable here, maybe I should have said if y equals e to the t, y prime also equals e to the t. But there's this k here, so it could be that maybe there's a multiple in front of the c, or it could be, you know, some multiple in front of the t, right? So it doesn't necessarily be just plain old e to the t. It could be some number times e, and maybe not t, but kt, where c and k are just constants. And we could actually check this. Like, if y equals c to the e, or c times e to the kt, let's take the derivative of this one. Let's just see what happens. Let's just check. Y prime would be, well, the derivative of e to the kt is just e to the kt, and then the chain rule kicks in, and that c just goes along for the ride, so the derivative would be c e to the kt times the derivative of kt. And of course the variable here is t, so the derivative of that is just going to be k, so that would be ce to the kt times k. And let's see if that works up here, because this says y prime equals k times y. Y prime equals k, and here's y right there, right? That's y. So this is saying y prime equals k times y. Right? Here is y. That's y right there. So we just found out that y prime equals k times y, so that this is a solution to this differential equation. Okay, so with that in mind, let's just write something here. So if y of t, so y is a function of t, equals c e to the kt, then let's see what y of 0 is. When time is 0, we get c e to the 0. E to the 0 is just 1, so that equals c. So this means our initial value, the value when time is 0 is c. So we have y of 0 is just c. So where we have the solution here, I'm just going to call this y of 0 initial value. And then you'll see a few different ways that this formula is given. So if you look over here, for the c here, I just put y of 0. So this right here, this formula is one that I'll typically use. There's 3 formulas, they're all the same, just different notation. So this one is like the general formula that you'll typically see. This is a general formula. This is one that I will use the most. And it's just saying y of t equals y of 0, the initial value of y, times e to the kt. Now this says the same thing, but this p a lot of times stands for populations. So population at time t equals p naught. It says p with a subscript 0, which is often called p naught. It's the same as p of 0. If I put a p here, it's the same as the population at time 0, but this notation is pretty popular. P naught e to the kt. You use this, a lot of times you'll see this when people are talking about a population. And then this other one, m of t, is m naught e to the kt. A lot of times that one comes up when people or books or resources are talking about mass. So these are all exactly the same. And because of that, I'm just going to use this for all of the problems. So you can just see y, whatever y is, the value of y at time t equals the initial value times e to the kt. A little note here I wanted to mention to you. For this one here, I'm going to use this form here, this format for the population. So this is just saying, it's the same thing. This is just instead of a y, we have p for population. For this example, I want to use population so that it means something. This is just saying p prime, right? This is just p prime dp dt, the rate of change of p with respect to t is equal to k times p. So it fits this format, it's this differential equation. The change in population is proportional to the population. So if that's true, then we could say this. We could say this implies that 1 over p times dp dt equals k, right? So all I did here is I took this equation, multiplied each side by 1 over p. So I got 1 over p here, 1 over p here, and the p canceled. Okay, and then one more thing from here, we could say this. We could say that dp dt divided by p is equal to k. And again, this is just algebra, right? Isn't this the same? dp dt divided by p is the same as dp dt times the reciprocal of p, which is 1 over p, which is right here. But then this will make the name make more sense. So you can see this k, this is the growth rate divided by population size. Right, because we've got the growth rate right here divided by the population size. And what that is called is the relative growth rate. Relative growth rate K. Now I think we're ready to try a problem. So our first problem here, example number 4. In the 9th edition, this is actually on page 245. So for the 9th edition, this would be page 245. But it's still problem number 2. The problem talks about the E. coli bacterium, and it mentions that a cell of this bacterium divides into 2 cells every 20 minutes, and the initial population of a culture is 50 cells. Okay, so this means, let's see, we start with 50 cells, so we could say like y of 0 equals 50. And we'll use y of t equals y of 0 e to the kt. And remember, this is the general formula which is the solution to that differential equation, dy dt equals ky. So that differential equation models this situation. So we're just going to use this general formula to solve the problems that they're going to bring up in this question. The first question they ask is they want us to find the relative growth rate. So if you remember, the relative growth rate is k. And we can find this because we do know a couple of things. We know that we're starting with 50 cells. We do know that a cell will divide into 2 cells every 20 minutes. So we can start off with our formula. Y of t equals y of 0 e to the kt. And if we're going to start with 50, I'm going to start with 50. Our initial amount is 50. Well, that means that after 20 minutes, we'll have 100. And then when I'm looking at the questions, they're asking us about time in terms of hours. So we probably should use hours instead of minutes. So for 20 minutes, we should probably use 1/3 of an hour. And again, I'm only doing that because I'm looking at these other questions. And for instance, part C is asking us to find the number of cells after 6 hours. So I'm just going to use hours for this. So looking at these conditions, we know that if we start with 20 cells, we start with 50 cells, we're going to have 100 cells 20 minutes later. And so the time is really, I'm going to put 1/3. So once we have this set up, we can just solve this for k, right? So what we could do is divide each side by 50, because I want to get at this power, I'm going to need logarithms, but I need to get rid of the 50 so I can use logarithms. So I'm going to divide each side by 50. So what we would get is I divide each side by 50, I'll get 2 equals e to the 1/3 k. All right, so I'm just dividing each side by 50. We need to get this number out in front of the e, because our rules of logarithms, we have this rule that says the natural log of a to the b is equal to b times the natural log of a. So you notice we have this natural log of the base. So I can't take the natural log right here. I have the natural log of 50 times the base. I need the base right here so we can take the natural log. So at this point, we can take the natural log of each side and say the natural log of 2 is equal to the natural log of e to the 1/3 k. And we wanted to do this because we need to get at this power. So then this can come down. We can use this rule now. So the b comes down. So this gives us the natural log of 2 equals 1/3 k times the natural log of e. And we know what the natural log of e is, right? Natural log of e is 1. Because remember, it's sort of like there's this little base e, and this question says what power do I raise the base to turn it into e? So it's going to be 1. So this is just 1. So basically, we just have the natural log of 2 equals 1/3 k. So if we want k, we can multiply each side by 3, and we get k equals 3 times the natural log of 2. And just for this problem, to make this one easier to work with, I'm going to use this rule one more time, but backward this time. So I'm going to bring the b up here. So in this case, I'm going to bring the 3 up here. So we'll get k equals the natural log of 2 cubed, which means that k equals the natural log of 8. So k is the natural log of 8. So the relative growth rate k is the natural log of 8. And I'm going to just leave it as the exact value. So, you could put it in your calculator and figure out what the natural log of 8 is. But I'm going to purposely leave it as the exact value so that when we start plugging it in here and coming up with a mathematical model, it'll be a little bit easier to use. Okay, so once we've got this, then question B says, find an expression for the number of cells after t hours. Well, we've got everything we need now because we've got our initial amount and we've got k. So a lot of these questions won't actually ask us they won't explicitly say to find the relative growth rate, but we'll do that because we need it in order to find the model for this. So in this case, like I said, they say find an expression for the number of cells after T hours. So they want us to figure out the constants we need to plug in. We've already got this one. We know this is going to be 50. We know K. So if we just start plugging things in here, we will get y of t equals 50 e to the k, and k is natural log of 8 times t. And here's where we need to recall something. There's something that we learned before. We said e to the natural log of x equals x. In an earlier section, we actually did a little proof of this. But basically, you could, just to verify it on your calculator, if you ask your calculator what e to the natural log of 5 is, it's going to tell you 5. And we're going to use this a lot right here. So when we get here, I'm going to just write this a little bit differently, just so we can make sense of something here. I'm going to write this as e to the natural log of 8, and then that raised to the t. And this is okay, right? Because think about what you know about exponents. If I have x squared cubed, remember from the good old days in algebra, we learned that we multiply those. It's x to the 2 times 3, right? 2 times 3. So really all I'm doing right here is just doing this backward, but I'm doing it purposely because then I can use this right here. E to the natural log of 8, that's just 8. So then I can say this is equal to 50 times 8 to the t. And then this is our expression that gives the number of cells after t hours. Now be careful about this. I can't just multiply these together, right? I can't just say y of t equals 400 raised to the t. This is the base, right? 8 is raised to the t, and then we multiply by 50. So these can't be combined. Okay, so that is part B. Part C just says to find the number of cells after 6 hours. Well, that's going to be pretty easy because we've got part B. We can use part B. So this gives us the number of cells, right? Y is going to be the number of cells after t hours. So after 6 hours, pretty easy here. We just say, so y of 6 equals 50 times 8 to the 6th power. And if you punch this in your calculator, you will get 13,107,200. So it's a little bit scary to think about, but we can see that after 6 hours, we have over 13 million cells. Then part D of this question asks us to find the rate of growth after 6 hours. So we basically are going to need to take the derivative, right? Here's the population, so we want to find the rate of growth. We're going to have to take the derivative of y of t. So in this case, we're going to get y prime of t equals, well, remember this 50 just goes along for the ride, and this is an exponential function, right? So we know this. We know that if y equals a to the x, we know y prime equals a to the x times the natural log of a, right? That's the general formula that we typically use or we typically see. So in this case, our variable, of course, is t, and our base is 8. So the 50 is a constant, so it just goes along for the ride. Well, we take the derivative, so we're going to get 50 times 8 to the t times the natural log of 8. So that will give us the formula for the growth rate. So the rate of change of the population with respect to time. And actually, I need to look a little closer to that question. It said after 6 hours. So once we have the formula, then we can just plug in 6. So really they're looking for the growth rate at 6 hours. So they're looking for y prime of 6, which is going to be 50 times 8 to the 6th power times a natural log of 8. So let's see, this growth rate gives us, if you punch this in the calculator, we are going to get 27,255,656 cells per hour, right? It's a growth rate. So the rate is going to be this many cells per hour. Okay, which actually sounds a little bit terrifying, but that's just a lot of cells per hour at that point. Remember that with population models, at some point the growth rate will slow down, and you'll get what's called an inflection point, and it will go from exponential growth, where it will get to a spot where it will level off as you reach the carrying capacity of the environment. So there's only so much space and so many resources and food and all of that stuff. So that all comes into play later. That's not something we're talking about right here, though. Then the last part of this question says, when will the population reach 1 million cells? Well, all these questions can be answered because we have our formula right here, right? This is our mathematical model for this situation. So all we have to do is set this equal, right? We'll set this equal to 1 million and solve for t. So that's what we can do on this one. So for part E, we just take our model and set it equal to 1 million, and then we solve that. So I'll just start here again. So y of t equals 50 times 8 to the t. This is our model. This is the population at time t, where t is in hours. So we set the population equal to 1 million. And then we solve for t. So of course, what we're going to have to do first is get rid of this 50, because remember, we are going to have to solve for an exponent. So we're going to need logarithms here. So we can just get rid of the 50, divide each side by 50. So divide by 50, divide by 50, that goes away. 1 million divided by 50 gives us 20,000. So 20,000 equals 8 to the t. And this is where we can take the natural log of each side. The natural log of 20,000 equals the natural log of 8 to the t. And of course, we're taking the natural log because we want to get at this exponent. Now this can come down as a multiplier. So we get the natural log of 20,000 equals t times the natural log of 8. And then, of course, we want t. So we just divide each side by the natural log of 8. That will cancel. And we'll get t equals the natural log of 20,000 divided by the natural log of 8. And remember, there's nothing to do here, like there's no canceling. Natural logs don't cancel. These numbers don't cancel. We just punch it in the calculator just like this. And what we'll get is roughly 4.76 hours. And just as a reminder, we don't cover significant digits in calculus. So some of these answers may seem a little strange to you if you've taken physics or chemistry and you've already talked about significant digits. So just keep that in mind. Because we don't officially cover that here, I won't really stick to any particular format about significant digits. The next question we take a look at is, again, out of the book. This one in the 9th edition is page 246, and it talks about the half-life of strontium-90. But first, we need to talk about what that means when we're talking about half-life. So to start talking about half-life, let's talk about carbon-14. So carbon-14 has a half-life of 5,730 years. So what does that mean? Well, there's different isotopes of carbon atoms, and there is an isotope means that they have the same number of protons but a different number of neutrons. So we have, like for instance, carbon-12 atoms and carbon-14 atoms. Most carbon atoms are carbon-12. In fact, it's something like 1 in a trillion carbon atoms are carbon-14. But carbon-14 atoms are not stable, so they will decay. And when they decay, a carbon-14 atom turns into a nitrogen-14 atom. Now this is something, when you're in your chemistry class, you'll get into a lot of details about this. So I'll give you kind of a brief overview, but really your chemistry professor will be way better qualified to describe exactly the detail behind it, and maybe even physics. But in math, we just have to have the basic concepts down so that we can understand radioactive decay and work on these sort of problems that can be modeled with these differential equations. So in the atmosphere, there's these carbon-12 and carbon-14 atoms, and they get absorbed into plants through photosynthesis. So the plants take in this carbon dioxide, and it has carbon-14 and carbon-12, and then animals eat the plants. So at any point, there's a ratio of carbon-14 to carbon-12 that's constant in living creatures. So you have this ratio of carbon-14 to carbon-12. And the carbon-14s the carbon-14 atoms decay, but the plants are always taking in more carbon-14, and the animals that eat the plants, so they are constantly taking in more carbon-14. So as they decay, they're always being replaced. So we have this ratio of carbon-14 to carbon-12 that's fairly constant, as long as, in this case, our woodlands friend here, I have no idea what this is, but you can see it's a very happy, he's smiling, he's happy because he's eating these delicious berries. And these berries have a constant ratio of carbon-14 to carbon-12, then he ingests them, so then he also has a constant ratio of carbon-14 to carbon-12. So the carbon-12 atoms are constant, so they don't decay, they stay, or not constant, they're stable, so they stay carbon-12, but carbon-14 is always decaying. So let's say our friend here is just enjoying these berries so much, he thinks just for a second, wow, that sounds a little bit like a truck coming. And then we have the next scene. It's not a very good scene. It actually was a truck coming, and our friend is a little bit flatter than before, and you know what this means in cartoon characters? He is no more. So he has this carbon-14 to carbon-12 ratio, and now there are no more carbon atoms coming in, right? He's not eating anything. So at this point, these carbon-14s are decaying slowly over time, right? But carbon-12 is staying, it's stable. So this ratio is changing. And because the rate of decay of carbon-14 is known, in fact, that's what we talk about the half-life, we said that the half-life of carbon-14 was 5,730 years. So that means if you have a clump of carbon-14, after 5,730 years, half of it will have decayed. And then after another 5,730 years, half of the remaining will have decayed. So because of that, we can look at this ratio. Years down the road, somebody could find a part of this animal and look at the ratio here and know how long ago was it that the animal stopped eating or ingesting carbon, or in other words, how long ago did the animal die. Now with carbon-14, you're typically limited for carbon-14 dating to about 50,000 years. And there are some exceptions to that. And it's also usually accurate to within about plus or minus 30 years. So if you want to date something older, like older than 50,000 years or so, you just have to use some other element. So as an example, for one of the questions in the homework talks about dating dinosaur fossils, and for that they use potassium-40. Potassium-40 has a much longer half-life of carbon-14, and it turns out to be approximately 1.25 billion years. Just one more thing, when I talk about carbon-14 decaying, it doesn't decay like it just evaporates or disappears. It decays into nitrogen-14, and that is something you'll learn the details about in a chemistry class. But now I think we are ready to try problem number 8 in the book, which talks about strontium-90 and has a half-life of 28 days. So let's take a look at that one. So it says, for part A, it says a sample has an initial mass of 50 milligrams. Find a formula for the mass remaining after T days. Okay, so for part A, we do what we do on most of these problems. It comes down to our equation. And if they give us the half-life, we can find everything we need here. Right? I mean, we can find K, which is what we need. If the half-life is 28 days, all that means is that whatever I have initially, after 28 days, I have half as much. So in this case, it says we have initially 50 milligrams. But even if we didn't know the initial amount, it wouldn't matter. I could use y of 0, and after 28 days, I'm going to have 1/2 y of 0, right? So you could use that. But in this case, they tell us that initially we have 50, so I'm going to write this. So initially there's 50, and the time t is 28 days, right? Initially we have 50 milligrams, but 28 days later we have 25. So we just need this to get started. And to find k, I need to take the natural log, but first I need to get rid of this 50, right? I need to get rid of that. I need to have the base isolated before I can take the natural log. So I'm going to divide each side by 50. All right, just divide by 50, divide by 50. And then we'll end up with 1/2 equals e to the 28k. And this is where I said, sometimes you don't have the initial amount, but you just want to find k. Well, think if I would have put y of 0 and 1/2 y of 0. Once I divide each side by y of 0, I'll end up here anyway, right? So you could even just put a random number in here, 100, 28 days later I have 50, right? Or 2, 20 days later I have 1. Anything like that to get started. If we have the half-life, we can find k every time. So now to find it, I'm going to take the natural log of each side. And then do the same as last time. Once we have this, I can bring this down because of the rules of logarithm. So get natural log of 1/2 equals 28k times the natural log of e, right? Times the natural log of e. But we already know the natural log of e is just 1. So when I bring this down, I have 28k times natural log of e. This is just 1. So I'm just going to erase that. I don't even need it. So basically I have this. So now to solve for k, we could divide each side by 28, but I'm going to purposely do something different because it'll make our equation nicer to work with. So what I'm going to do instead, I'm just going to say k is equal to, I'm going to multiply each side by 1 over 28. So I'm going to say k is equal to 1 over 28 times the natural log of 1/2. Right, so I switch these around too, but basically I multiply this side by 1 over 28 to get k, multiply this side by 1 over 28 to get this. So once we have k, then we can go back and plug that into the original equation. So I have y of t equals y of 0, which is 50, e to the k, which I have 1 over 28, times the natural log of 1/2 t. Okay, and I'm just going to algebraically manipulate this. These are being multiplied together, right? 1/28 times natural log of 1/2 times t. So if I wanted to, I could write it like 50 e to the natural log of 1/2, right? 1/2 times t over 28. Right, so I put the 128 over here by the t, and you multiply, this is like t over 1, so I get this. But I really want this because I want these two to be grouped together, because then I'm going to purposely group these like we did before, right? Just like we've said before, if I have x squared cubed, that's x to the 6, because it's really just x to the 2 times 3. So I can, if I have it like this, I can put these parentheses here. All right, actually, maybe I should have said this is x to the 2 times 3, right? And then we're going to use that other rule. It says e to the natural log of x is equal to x. We use that right here. So this is really just 1/2. So we really get y of t is equal to 50 times 1/2 t over 28. And then this is our formula. And the formula is nice. You can sort of see that the half-life is right here, like half. 28 days is the half-life. So just think what we've got. Initially we had 50 milligrams. After 28 days, this would be 28 over 28, which is 1. So we'd have 50 times 1/2, right, which gives us 25. After, say, I'm just going to make it an easy one, 56 days, After 56 days, we'd have 56 divided by 28, which is 2. So we'd have 50 times 1/2 squared, or 50 times 1/4, right? So you can see it's like halving each 28 days. The amount of strontium-90 gets halved, right? Because the half-life is 28 days. So I like this formula. To me, this is the best one. But I'm just going to tell you, when you look in the book, they're going to do something kind of weird. So just so you're aware of it, when you look in the back of the book, they do something else. And it works, but what they do is they write 50, and then they write, instead of 1/2, they write 2 to the negative 1. Okay, again, I don't think this is as good of a technique, but they do it. Right, because isn't 2 to the negative 1 is just 1 over 2 to the positive 1, which is 1/2. And then here they multiply through, just like we did here. So in the book, when you look in the back of the book, it says, like, they'll have y of t equals 50 times 2 to the negative t over 28. Okay, algebraically they're the same. I just don't really like this one. This one, to me, is better because you can see it's a half-life. There's a half-life right there. So anyway, either one is okay, but I'm going to usually write mine this way. All right, so once we have our model, then we can answer questions. So question part B says, find the mass remaining after 40 days. Well, it's not a problem at all. Here's our formula for the mass at any time t. So after 40 days, you would say y of 40 is going to be 50 times 1/2 to the 40 divided by 28. So if you punch this in your calculator, be careful, depending on how your calculator works, if you raise this to this power, you may have to put this in parentheses, just so that it does the order of operations correctly. And if everything works out, at this point, you should get right around 18.6 milligrams. Okay, so that is the mass remaining after 40 days. We started with 50 milligrams. 40 days later, we're at 18.6 milligrams. Then part C says, how long does it take the sample to decay to a mass of 2 milligrams? Okay, so once again, we come up here. Now, where does the 2 go? Well, t is time, right? So it doesn't go there. So 2 milligrams is this. This is the mass, right? This is the mass. So I plug in a 2 here, and then I solve for t. So for part C, we would say 2 equals 50 times 1/2 to the t over 28. So once again, if we're solving for an exponent, we're going to need logarithms. And so you should take a second, just pause and see if you can come up with this one. Okay, so try it out, solve for t, and then check back. Okay, are you still sitting there? Stop sitting there, press pause, try this one out. All right, hopefully you tried this one out. As you know, the only way to get better at this stuff is by doing this stuff. So for this one, I'm going to isolate that 1/2, so I have to divide everything by 50. So that's gone. 2 over 50 is the same as 1 over 25. 1/2 t to the 28. And now to get at this thing, I need a log or a natural log. I'm just going to keep using natural log. You can use log base 10 also, common log, that works okay. But I'm just going to use natural log, so I get natural log of 1/25. There's natural log of 1/2 to the t over 28. At this point, because I have the natural log, I can bring this down and get the natural log of 1/25 equals t over 28 times the natural log of 1/2. Okay, just a lot of algebra here. I want to get t by itself. It's being multiplied by natural log of 1/2. So I'm just going to divide everything by natural log of 1/2. That would give me the natural log of 1 over 25 divided by the natural log of 1/2 equals t over 28. Right, I just divided. I've got an equation here. I divided this side by the natural log of 1/2, which left me with this, divided that by the natural log of 1/2, which left me this. And now I basically need to get rid of the 28. So t has been divided by 28, so what I'm going to do is multiply each side by 28 to get rid of that. And that would give me t equals natural log of 1 over 25 divided by natural log of 1 over 2 times 28. And if you punch it in your calculator, you should get something like right around 130 days. So in about 130 days, these 50 milligrams will decay to about 2 milligrams. The last question asks us to sketch a graph of the mass function. So if you wanted to do this on your graphing calculator, basically you just have to go to your y1 in your graphing calculator and just type in 50 times 1/2 raised to the, of course it'll be x in the graphing calculator, x over 28. Again, depending on your software, you may have to put this in parentheses. Some of the newer calculators have what, at least for Texas Instruments, they call it math print. So this will automatically be in a superscript location, so it'll be up here. But if not, just put parentheses. And then what I did for the x-axis, if you put like from 0 to 200 for the time, and the mass in milligrams, you just need to go from 0 to 50, right? Because it started at 50. And the graph just does sort of what you would expect. It'll just kind of follow down like this. So we've got exponential decay. We've got one more here. And this is from the Lascaux cave in France. And there's some pretty amazing pictures here and these caves, considering how old they are, these drawings. I mean, if you look at what they say here, they say charcoal samples taken from the cave walls had a carbon-14 to carbon-12 ratio equal to 13% of that found in the atmosphere. So again, the carbon-14 atoms have been decaying, the carbon-12 have stayed steady, so the ratio has been changing, equal to 13% of that found in the atmosphere. What is the approximate age of the painting? Of the painting, it says half-life of carbon-14 is 5,730 years. So if you look online for these paintings, there's really quite a few of them from these caves here. But let's figure out how to do this one. So we know really that we're going to have to start with our model from before, right? So I'm just going to write down what we've already been working with. We know y of t equals y of 0 e to the kt. Y of 0 is the initial amount. And so what we really need to do first is to find k. We need to find k so that we can start making this model work. And we can find it because they gave us the half-life, right? They gave us the half-life. Half-life of carbon-14 is 5,730 years, so we can plug that in for our model here to solve for k. So we just have to make up an initial amount, and we know that after when time is 5,730 years, y of t will be half that. So we could do it like this. We could just say, well, I'm just going to say initially we had y of 0, and after 5,730 years, we had half that. So time is 5,730, and now the amount we have is half the original amount. This is what I was talking about before. So from here, we're going to just divide each side by y of 0, right? So if you divide each side by y of 0, they just cancel out, and so you end up with 1/2 equals e to the 5,730k. Here's where, just like before, we have the natural log come in. We have the natural log of 1/2 equals the natural log of e to the 5,730k. And of course, this is going to come down. You see how this is all very familiar now because we do this on all of these problems. 5,730k times the natural log of e. But once again, what is the natural log of e? Just 1, right? So I don't even need to write it. It's just 1. So I'm just going to get it out of here. Okay, so then for k, if I want to get k by itself, I'm going to multiply each side by 1 over 5,730. And that would give me k equals 1 over 5,730 times the natural log of 1/2. All right, so now I've got k, so we can come up with our model now. So y of t equals y of 0 e to the k. Now look at what k is. K is this times this. So multiplication is commutative. I can switch these around. So I'm going to switch them around just because it's going to make what we need to do next easier. Times 1 over 5,730, then times t, right? All I'm doing is plugging that into this right here. I'm just plugging k in. This is k times t, k times t. But then I'll do one more step here. This is equal to y of 0 times e to the natural log of 1/2. And I'm just going to do this. I'm going to write it like this, like a parenthesis. And then I'm going to multiply these together and get t over 5,730. Right here, we know e to the natural log of 1/2 is just 1/2. So this is going to give us y of t equals y of 0 times 1/2 t over 5,730. Okay, so now we've got a model. And it looks like the same one as before, right? So we've got the 1/2 here, we've got t over the half-life. So in this class in calculus, when we're asked to find this, we know what they're going to look like, but we can't just plug it in like we would if we were an algebra student. If we were in algebra class, we'd start here. They'd say, here's your formula, here's your model, and now, answer a few questions. But in calculus, we develop this, right? We develop this by starting here, and then we find k and we come up with this. So we have to be able to come up with this process to get here. Starting from here, this will be our initial point. This is where we go by using the fact that the half-life in this case is 5,730 years. So we get here, and then we make sense of this part. So what we've got is 13% of that found in the atmosphere today. So if we think about right here, what that is saying is that initially we had a certain amount y naught, right? That was our initial amount. But what we've got now, is 13% of that. So we've got 13% of y naught. Well, isn't 13% of a number just 0.13 times a number? So here's our initial amount. Now there's 13% of that left. And I can plug in all the rest. So I've got 0.13 times y of 0 equals y of 0 times this. So I could just divide each side by y of 0, right? Divide by y of 0. Those would cancel. And that would give us 0.13 equals 1/2 t to the 5,700 and t over 5,730. This is going to allow us to solve for t to figure out, well, how much time did it take? How much time does it take for this initial amount to become only 13% of its original amount, right? We're solving for t. So from here, we can take the natural log of each side. And then, of course, what we're going to do, take this down. So we get the natural log of 0.13 equals t over 5730 times the natural log of 1/2. Okay, I'm going to continue this up here. So we're solving for t, so I'm going to first divide each side by the natural log of 1/2. So I would get the natural log of 0.13 divided by the natural log of 1/2. I guess I can just use 0.5 since we're using decimals in the numerator. That equals t over 5,730. We want to solve for t, so I need to multiply both sides by 5,730. And that would give me t equals natural log of 0.13 divided by natural log of 0.5, and then that times 5,730. And if you go through that on your calculator, you should get t is roughly equal to 16,860. I'll just say 66. I'll run it to the nearest year. Remember, we don't expect this to be precise to the year, right? I mean, it's not going to be precise to this. I mean, I don't have confidence that this 6 is really a 6, right? But it should be in the ballpark of this. And we have done this with just this model. This model is sort of assuming that the carbon-14 to carbon-12 rates remain constant through this time. Now, what happens in reality is the model will be tweaked somewhat by calibrating for carbon-14 differences at times in the past. And calibrating is done by using tree rings and also by looking at caves, and you have those stalagmites from the floor and stalactites from the ceilings, and they can use that to go back and make little tweaks, little tiny tweaks that we don't have here. Our model doesn't allow these tweaks, but if you are researching, you wanted a more accurate number here, you do these little tweaks, but we get really close. So if you look this up on Wikipedia, I'll tell you what they do. They have their estimates a little better, I'm sure, because they're tweaking it. Our model is assuming everything stays steady, but it's still pretty close. They say it's about 17,300 years old. So we're not too far off for a model that's assuming everything's constant forever, right? So not bad. And the oldest cave drawings, just in case you're interested, the oldest ones that are known so far are found in Asia and Europe, and they're about 40,000 years old, which is pretty crazy. 40,000 years. It's a long time. So these are pretty old here too, but they're still kind of newbies compared to the oldest ones out there. Okay, but this should give you what you need to get started on everything except for Newton's law of cooling. We will save that for next time, but for now you should be ready to go on everything in the homework that does not involve Newton's law of cooling. So give those a try and let me know if you have any questions.